Now we're going to do some reactions. These are really important because 6, 7, and 8 is all straight reactions. Um, and these are simple ones that you should know how to do just for the purposes of the future of the class. Okay, so the first thing is you got to figure out what the acid and what the base is. Okay, so I do these problems by just figuring out what the base is. And from there, I can figure things out. So here's what I mean. Bases are going to donate electrons and pull protons. Sometimes in an acid-base reaction, you have no protons to pull. You just have a donation of electrons. So the first question I want to ask myself is, what can donate electrons? Which one of these has a lone pair to give, right? BF3 is full. If you look at its placing in the periodic table, it's got 3 spots. Those fluorines are occupying those spots. So oxygen has to be the base because it's the only thing with lone pairs to give to the bromine. So the next important piece, we found the base, acid, is the arrow flow. The arrows go from the base, the electrons on the base, to the acid or the proton on the acid, from here to here. So the final structure will look like this, right? So this is more of a Lewis acid-based question because they kind of stick onto each other like Legos, right? There's no pulling of protons, but there is an exchange of electrons, right? The acid accepted electrons, the base gave electrons. Let's do this one. This one's interesting. First, we got to figure out which one of these has electrons to give away. So it looks like this oxygen does, but in fact, it is not, because this oxygen has an acidic hydrogen, as in this can be pulled off. This will be our acid. I'll explain why. Okay? Even though the oxygen is electronegative, it has lone pairs, it does not mean it's going to be the base. We can't jump to that conclusion. One, a base would have to either just donate electrons or donate electrons and pull a proton. So for me, I look at this problem and I first identify, okay, this is going to be more of a Bronsted-Lowry question, right? Because I see this proton here, which tells me that this is probably not going to be the base because it has a proton that's obviously, from the drawing, it wants to be pulled off. But the question is, where did the arrows come from? And in fact, when you put a reaction in solution, what happens is that this metal and this carbanion kind of separate. In solution, they dissociate. And so in reality, when you have a carbon chain attached like a metal like this, just treat it like a carbanion. So it's going to be a base, right? It's going to be a very strong base. It's going to come in here, right? Arrow from the electrons to the hydrogen. And we have to do another arrow to show that the bond is breaking. Doesn't go the opposite way. It always goes from the most electron density to the least. Let's go here. Aqueous barium hydroxide. When we do these metals, boom, just treat it like an anion and just ignore what's there. Okay, this looks scary, but it'll be okay. Hold on, my pen is going out of power. Okay, so this aqueous barium hydroxide, the barium removes itself in solution, so now we have the OH minus as our base because it has a negative charge. That's safe to assume, given this problem. And this carboxylic acid is going to be our acid, okay? And so the base, like what bases do, Arrow is going to come from the electrons to the proton, if there's a proton to get pulled off, or to the acid, pulling that hydrogen and then moving these electrons onto the oxygen. Same thing, aqueous barium hydroxide. This big old structure is going to be our acid because this is more negative. So we can say that this is our base. So this base is going to come over here. Arrow is going to pull this hydrogen off, moving these bonds onto the oxygen, then creating your final structure. Then we have this last one. Again, we see these metals. Ignore the metal and give whatever the end element is a charge. And when it says in ethanol, that means that this is the solvent. It's inside. It's in ethanol. So we're not, for now, we don't care about the solvent. And we're working with ethyne. Ethyne is our other reactant. So here's an issue with this one, though. We've identified our base, right? We know it's a base because it has a charge, and this is our acid. So the question is, can this base pull this acid? And the answer is no. This base is not strong enough. The strong enough bases are carbon ions, hydride ions. Ooh, what is this? Hydride ions, and NH2, NaNH2, sodium, whatever that is. So sodium, potassium, doesn't matter. These are strong enough to pull off a hydrogen on a terminal alkyne, is what it's called. Nothing else is strong enough. If you see this question on the exam, this is not strong enough. It is not going to work. So these are just some good examples for acid-base reactions. I hope that made sense.